Okay, so coordination compounds. This is totally different. This is totally foreign to anything we've talked about so far, and you're gonna hate me for this. It's probably not on the AP exam this year. What? Why am I teaching it to you? Well, the reason I'm teaching it to you is because the workshop I went to this summer, one of the people who taught that workshop was a chemistry professor, and he said, look, in first-year college chemistry, they usually talk about this. So even though it's not on the AP exam, I thought it would be a good idea to talk you through it because I want to give you the experience that you'd be getting typically with a first-year college chemistry course, okay? Now, granted, that guy, that was his thing, coordination compounds, so he kind of had a vested interest in us teaching it, I guess, because he likes it. But I think he's right. In my experience, what I've seen from first-year chemistry curriculums, it seems like they at least touch on this. So, and that's all we're really going to do. Is, I mean, we're covering it in a day. So, but there is some really cool stuff you can do with this. And at the end of the year after the AP exam, we've got this really cool lab we're going to do that involves coordination compounds that I think you'll have some fun with. So, anyway, so here it is. And this is going to be whirlwind, very brief. And what you actually need to know with this is not that bad, okay? But it's going to be a little complicated at first. So a complex is when you have a metal atom, and it's actually bonded to a group of molecules or ions. So we're talking about covalent bonds here, okay? Which is a little unusual for a metal, all right? I think I've told you up to this point that metals form ionic bonds with nonmetals, and that's basically what they do. Well, I lied a little bit. But this is a special kind of chemistry, a special category that we just haven't really talked about yet, okay? So the example here, what you have is this cobalt, and it's actually bonded chemically or covalently bonded to a couple of chlorines and 4 NH3 molecules, okay? Which is a little strange, all right? You've got these 4 molecules that are actually bonded to this one atom, and then the chloride's also bonded to it. That's called a metal complex, okay? If it has a charge, then it's called a complex ion, okay? And compounds containing complexes are called coordination compounds. So you're going to see all of these terms that sort of mean the same thing, but they're just different nuances of the same idea, okay? So metal complex, complex ion, coordination compound. We're basically talking in all those cases about a metal atom that's surrounded by groups of molecules or ions that are called ligands. Okay? So these complex ions are soluble in water, and it's because they're ions. They're soluble in water. Water likes ions, right? So you've got the ion-dipole interactions. So these are all, if they're ions, they're all soluble, okay? And usually they're very colorful. So that makes this kind of chemistry fun because you've got all these bright colors that occur. The molecules are ions that coordinate to the metal, and coordinate is basically just another way of saying they're covalently bonding to the metal. They're surrounding it. Those are called the ligands, okay? Now the ligands all have certain things in common. Let's see if you can figure this out. What do all of these kind of have in common here? Okay, they're all nonmetals or polyatomic ions, right? Which, I mean, they're still nonmetals even though they're polyatomic ions. There's one other really significant fact here, or a significant part to the structure. Okay, they all have lone pairs of electrons, right? Okay, and so, you know what, I'm just realizing I may not have the Lewis acid and base stuff in this set of slides. I'm going to have to look and see. If not, I'm going to have to talk to you about Lewis acids and bases. I'll tell you what, I'll just talk to you about that right now in case, well, here, let me see. Actually, I think what I'm going to do is change my mind like 4 more times and then decide. Okay, it's not on here. So they're usually anions or polar molecules, and they always have lone pairs of electrons because ligands are what we call Lewis bases. Have we? I never can remember from year to year. Have we talked about Lewis acids and bases this year? Okay. So this idea, it's not that complicated of an idea. The acid-base idea we've talked about so far, got something like HCl. We've said that an acid is something that's going to donate a hydrogen or a proton, an H plus, in a solution, right? So you put this HCl in solution, it splits apart, and now you have an H plus in that solution. So that makes it an acid because it increases the concentration of H plus in the solution. That's called the Bronsted-Lowry definition of acids and bases. Okay, this right here, the Lewis acid-base definition, basically just means that you've got one thing here that is a proton donor and another thing that is a proton acceptor. Okay, so no, I'm sorry, that's Bronsted-Lowry. Let me try that again. We focus on electron pairs, not on.
Repeat, Jan, if you're in the building, please dial extension 26226.
Not on the proton. Okay.
Repeat, Jan, if you're in the building, 26226. Thank you.
So you've got an H plus here, okay? H plus has no electrons, right? So if it bonds with something else, it would be an electron pair acceptor, okay? Because in order to bond with anything, for example, maybe a water molecule, and this is a real simple example here. If you've got an H plus, if it bonds with a water molecule, it's going to accept basically a lone pair of electrons from the oxygen here in order to form H3O plus, okay? So this we would call the Lewis acid because it's an electron pair acceptor, okay? Now oxygen in this case is the electron pair donor, so in this case we would call the water the Lewis base as this reaction is occurring, okay? And so then those two would combine to form H3O plus, okay? In that instance, the H plus would be the Lewis acid, the H2O would be the Lewis base, okay? So all of these ligands here are Lewis bases because they are proton donors. I keep saying protons, I'm sorry. They are electron pair donors, okay? Just so used to the Bronsted-Lowry definition. So this, circled the wrong pair here. It's going to be the one from the nitrogen. So this right here can donate a pair of electrons to something else, okay? Right here, this nitrogen can donate a pair of electrons to something else. Chlorine has, several pairs of electrons it can donate to something else. So all of these can donate. And then what you end up with usually is you've got a metal ion, something like Mg2+, or I guess in the previous example we've got cobalt, and I think it's cobalt 3+, okay? So cobalt 3+ really doesn't have any valence electrons, okay? And so it can accept the electrons, the lone pair of electrons from the nitrogen, which makes this the Lewis acid, okay? The metal is going to be the Lewis acid, and then the ligand here is the Lewis base. Okay, so that's the idea of Lewis acids and bases. It's focusing on electron pairs rather than the H pluses and what the H pluses are doing. And it's a broader definition. By that definition, Fe3+ is considered an acid. Okay. Now, by the Bronsted-Lowry definition, that doesn't have any hydrogen with it. So how could that be an acid? Okay. But what happens in a solution is this Fe3+ actually will accept protons. Darn it. What's wrong with me? It will accept electron pairs from water, and it will form a complex, FeH2O6, 3+, okay? And when it does that, we would consider it to be an acid because it's accepting electron pairs from the water molecules that it bonds with, okay? So this actually will turn the solution a little bit more acidic when you put this in there, because what happens is some of these OHs on here, the hydrogen can come off, okay, of these OHs that the iron binds with, okay? So again, starts out very complicated here, and then when you see what you have to do with it, it's not so bad, okay? Many coordination compounds are brightly colored. So you can see here, just even depending on the number of ligands that it coordinates with. So this COCl3 with 6 NH3 is orange, with 5 NH3 is purple, 4 NH3 is green, and interesting. These are both the exact same formula, but they have different colors. Okay, and this phenomenon right here is actually what kind of led to the formation of this new science of coordination chemistry. Because the old way of writing these formulas, there was no difference between this green and violet right here, and people couldn't figure out, well, why is it sometimes green and why is it sometimes violet if there's the same amount of Cl3 or Cl and NH3 in both of these, okay? And so Werner, I don't even know what his first name is, but he's the one who kind of came up with the idea of coordination compounds in general. Alfred, okay, thank you. So was that somewhere else? Oh, it's in the book, okay. So basically what he realized was, so this first compound right here, it's got cobalt with 6 ammonia molecules around it, and then basically what you have there is a complex ion. So you've got this CO NH3 6, and that whole thing has a 3+ charge, okay? And then it's combining in an ionic compound, it's combining with 3 Cl minuses so that you end up with the CO NH36 Cl3, okay? So it's basically just an ionic compound. This is the cation right here, this whole big mess. And then this is the anion, okay? And you need 3 of those, obviously, to balance out the 3+ charge here, so you end up with this formula, CO NH36 Cl3, okay? But then you could also have one where you've got cobalt covalently bonded to 5 NH3s and 1 chlorine, all right? And so then you end up with an ion that, you know, looks like this, CO NH3 5 Cl. Okay, and if you add up the charges here, the reason that this is a 3+ charge is because cobalt has a 3+ charge. What's the charge on ammonia? If I just have NH3 gas, what's the charge on it normally? NH4 is a 1+, right? We know that's a polyatomic ion. NH4 is a 1+. So if I take away one of those hydrogens to make NH3, what would the charge be? Wouldn't be a 2+, because the hydrogens are a 1+ there. It's going to be neutral, right? If I take away one of the hydrogens, so NH3 is just a neutral compound. It doesn't have a charge, okay? So if I've got something here that has a charge of 0, it doesn't matter that I have 6 of those. They all have a charge of 0, so they're not contributing to the overall charge. This cobalt is a 3+, so then overall the ion is going to be a 3+, all right? But over here, this cobalt's a 3+. These NH3s are, you know, 0. But then this chlorine's a 1-. So what's the overall charge on that polyatomic ion? 2+, right? So then when it combines with chlorides, it's going to combine with 2 of them to form the ionic compound, okay? And then down here, you've got, now the cobalt is covalently bonded to 4 NH3s and 2 of the chlorides. That's going to end up with a charge of 1+, so then it's going to combine in an ionic compound with 1 of the Cl minuses. Now the reason that there are 2 of these is because there are 2, and I think I have a picture of this. Yeah, there are 2 possible orientations for this, okay? So you could have an orientation where both the chlorides are right next to each other, covalently bonded, or you could have one where they're actually across from one another, okay? And so that makes the cis, this is cis right here, and this is trans, okay? Cis basically means they're right next to each other, trans means they're across from one another. So then you look back over here, if it's trans, if it's in that arrangement, it's green. If it's cis in that arrangement, then it's violet, okay? So that's kind of the basic idea. That's where coordination chemistry came from in the first place, okay? No, not, you don't really need to know what his theory is. I just want you to know basically what coordination compounds are, so some of that was just a little bit of background on that. So palladium tends to form complexes with a coordination number of 4. One such compound was originally formulated as PdCl2.3NH3, suggests the appropriate coordination compound formulation for this compound. Okay, so if it has a coordination number of 4, then that means that palladium likes to have 4 things covalently bonded to it. That's basically what that coordination number means. Okay, so if you look back at the cobalt over here, this cobalt has a coordination number of 6. Okay, because in every single one of these, it's got 6 things bonded to it, right? Well, actually, I should be looking at this one. So it's got 6 things bonded to it here. Still 6 things here. It's 5 NH3s, 1 Cl. Okay. So that would be a coordination number of 6. So here, if the palladium has a coordination number of 4, then that means it's going to have 4 things covalently bonded to it. Okay. Now, most likely the NH3s are going to be part of those covalent bonds because they don't have a charge, so they're not going to form an ionic compound. Okay? So probably the way that we would want to write that formula now is PD NH3, there's 3 of them, okay? PD NH3, 3. But to get us a coordination number 4, we need to put one other thing covalently bonded on here, so that would be one of the chlorines, right? Now this is all in brackets. Palladium 2 has a 2 plus charge, right? That's what the Roman numeral means. So if we've got a 2 plus here and a 1 minus from this one chlorine, then overall this is a 1 plus charge for this ion. Does that make sense? That can be balanced out by the chlorine that's still left over here, okay? And so this ends up being an ionic compound with all of this right here having a 1 plus charge, and then the chlorine having a 1 minus charge. Okay? Okay, good question. So how do we know the coordination number? Good rule of thumb, and I put this on the reading guide too, a good rule of thumb is the coordination number is usually twice the charge on the metal atom. Okay? So for example, you might have noticed in the first example, the cobalt has a charge of 3 plus, and its coordination number was 6, 2 times 3. Okay? In that last example, the palladium is a 2 plus charge, and notice its coordination number is 4. Okay? So usually you can just double the charge, and that's the coordination number. Now that doesn't always work, but that's a good rule of thumb. Okay? All right. Sorry, go ahead. Because it's neutral, yeah. So you'd put the NH3, that would probably be on the other reason maybe is because the nitrogen is going to be maybe a little more electronegative because it's smaller, right? So you've got that nitrogen there, so, and honestly, I don't know this for sure, but it makes sense to me just looking at it that the nitrogen, because it's a little more electronegative, might tend to form the compound first, might be a better electron pair donor. It's more electronegative than the chlorine. Yeah, see, that's kind of a tricky one, but because it's smaller. Remember, nitrogen, oxygen, and fluorine are 3 of the most electronegative on the periodic table because they do the hydrogen bonding, right? So that would be my guess on that one, okay? It is kind of just one of those things that becomes intuitive after you look at enough of these. Oh, the chlorides are going to end up being the anions that combine with it to make it an ionic compound. Okay, this talks about Lewis acids and bases a little bit, and I already went over that with you, so we can skip that. So the metal ligand bond right here, again, the metal is always going to be the Lewis acid because it's the one that's accepting the electron pair. And then the ligand is going to be the Lewis base. Okay? Oxidation numbers, it would be good if you could, this is one of the things that I might throw on the test, is knowing the overall charge of one of these things. Okay, so for example, if you know your copper is a 2+ charge, and you know each of the NH3s is neutral, right? So then the overall charge must be a 2+. So you might have to do one of the two. If I give you the overall charge here, then I might ask you what's the charge on the metal atom, okay? And you wouldn't know that right off the bat because they're usually transition metals, so they can have different charges, okay? Or I might tell you the charge on the metal atom and ask you, what's this number? What's the charge going to be on the complex ion, okay? So we might go either way on that one. The oxidation number, the central metal in this whole mess, okay? These things are kind of crazy. So the oxidation number of the central metal here, which is, I think that's rhenium, that's what we're trying to figure out here, okay? So we don't know what this is, but we do know what the overall charge on the complex ion is because it has to be bonded to 2 nitrate groups in order to form a stable ionic compound. What's the charge on nitrate? That's phosphate. I think you're thinking phosphate on that. Yeah, it's a 1- charge, okay? So nitrate's 1-, and it took 2 of those to balance out the charge on the complex ion. So this is a 2+ charge. Does that make sense? Because we've got 2- charges with the NO3s, okay? So if that's overall a 2+, and this chlorine we know is a 1-, right? And the NH3 are all 0, they don't have a charge, then what does the charge on the RH have to be? Has to be a 3+. Does that make sense? Now notice again, this is a 3+ charge. Guess how many things are bonded to it? 6, twice the charge. Okay? Alright, so that's kind of how that works. That's not too hard, right? And then a complex ion contains a chromium 3 bound to 4 water molecules and 2 chloride ions. What is its formula? I think I want to focus here, and then the rest of this stuff you can pick up pretty easily from the reading, I think, but we'll make this maybe the last thing we do. So complex ion contains a chromium 3 bound to 4 water molecules and 2 chlorides.
Is there an administrator or a custodian that can unlock all the doors for the gym foyer area? The doors of the gym foyer area, is there someone that can unlock those, please?
Okay. So we've got chromium and 4 water molecules and 2 chloride ions. This one really isn't oh, yes it is. I'm sorry. It is going to be one where we have to figure out the overall charge. Okay. So we've got chromium. It's bound to 4 water molecules, so you'd write it like that, and then you'd put the chlorines at the end. Again, you might not know to do that. That's just kind of a convention thing, and I don't really care that you know how to do that part. Really what I want here is for you to be familiar with these. So when you see them, you're not scared out of your mind by something that looks way more complicated than anything we've talked about so far. Well, you see the names of these things. They're fun. So this is chromium 3, so this has to be a 3+, right? What's the charge on water? Yeah, H2O is usually a neutral molecule, right? So 0. And then the charge on the chlorides, 1- each, so that's a total of 2- here. Okay, so what's the overall charge on this complex ion? 1+. Okay? Which means it would probably, in solution, it would probably, or not in solution, but if it came into contact with something that had a 1- charge, it would probably form an ionic bond with it. Okay? So you could put, I mean, it could really be any 1- anion out here. Okay? But they're telling us about a complex ion, so we don't have to worry about that because it's okay that it's an ion in this case. Okay, we talked about coordination number already, and what that means. Usually it's going to be either 4 or 6. Geometries, I'm not too worried that you know that necessarily. Polydentate, that has some application in biological systems, and I may ask you a question about that. It's in your reading guide, so I'll let you look at that. I just want you to look at the names of some of these things. If you know how to name these, ethylene diamine tetraacetate. Yeah. Not as bad as it looks. I like how they say mercifully abbreviated EDTA, right? But yeah, if you know how to name these, you can make anyone think that you're like the smartest person alive. Because, I mean, look at that. That's ridiculous, right? And basically all it is just a bunch of prefixes and stuff like that. And I want you to look over how the naming happens, but I'm not going to test you on the naming on this test, okay? Because it's, again, I just want you to see it and be familiar with it. And I want you, most of all, I want you to be able to look at a name like this and say, oh, we're dealing with a complex ion here. I can tell because the name goes on for an entire line on the page, right? Okay, so that's basically it. And if you know that, then I'll be happy. The third section does talk about the rules for the naming, so if you're really interested in that sort of thing, you could look at it. But other than that, I want you to know basically what we went over as far as the oxidation numbers. I want you to know the biological systems stuff and how it's useful for biological systems, and then you should be good to go as far as our test is concerned. Okay? All right?